It is one of the strongest metals in the world. Every year, nearly 353,000 tons of titanium are produced. To obtain just 1 ton of the metal, approximately 11 tons of ore must be processed. The extraction process is so complex that production can take as long as 6 months. But how is a simple grain of black sand transformed into one of the strongest and most valuable metals on Earth? We visited one of the world's largest ilmenite mines to discover where titanium comes from and how it is made. For centuries, titanium represented something humanity had always dreamed of, a metal that was both lightweight and extremely strong, while also being capable of resisting intense heat and corrosion. When its surface comes into contact with oxygen, a thin layer of titanium oxide automatically forms over the metal. This invisible film acts like a protective shield, isolating the titanium from its surroundings and preventing it from continuing to react with corrosive substances. Titanium also has an exceptional strength-to-weight ratio. It can be as strong as steel while weighing about 45% less. Because it can withstand extreme temperatures and remain durable under enormous stress, titanium has become an essential material in the construction of modern aircraft. The metal was first identified in 1791 by British clergyman William Gregor, who discovered an unusual substance in black sand found in Cornwall, England. Several years later, in 1795, German chemist Martin Heinrich Klaproth identified the same element in another mineral. He named it titanium after the Titans, the powerful figures from Greek mythology. Identifying the element was relatively simple, but isolating the metal itself proved to be an enormous challenge. For more than a century, scientists attempted to produce pure titanium without success. When heated, titanium reacts easily with oxygen, nitrogen, and carbon, contaminating the metal and making it brittle. It was not until 1910 that American chemist Matthew Hunter managed to produce small amounts of nearly pure titanium through a complicated chemical method. However, his technique was extremely slow and expensive. Everything changed during the 1940s when Luxembourg-born metallurgist William Croll developed a more practical way to produce high-purity titanium metal. His technique, now known as the Croll process, involved first transforming titanium ore into titanium tetrachloride, and then reducing that compound with magnesium at extremely high temperatures. This discovery made titanium production much more efficient and opened the door to its use throughout modern industry. From that point forward, the metal began appearing in applications requiring materials that were exceptionally strong, lightweight, and capable of surviving extreme temperatures. Building a large aircraft requires an enormous quantity of titanium. A giant passenger plane such as the Airbus may contain approximately 77 tons of the metal. But titanium has one major disadvantage. Although its performance is far superior to that of many traditional materials, it can be approximately 15 times more expensive than aluminum. The high price is caused mainly by the complicated extraction and refining process. Turning mineral ore into usable titanium can take several months and requires numerous energy-intensive chemical and mechanical stages. But where does titanium originally come from? Titanium is extracted from naturally occurring minerals found in Earth's crust. The two most important sources are ilmenite and rutile, which contain high concentrations of titanium oxides. Unlike gold or silver, titanium is not normally found in nature as a pure metal. Instead of appearing as nuggets or veins, it is chemically bonded with oxygen and other elements inside rocks and mineral sands. Titanium is actually one of the most abundant metals on Earth. It makes up approximately 0.6% of the planet's crust, making it the 9th most abundant element. The problem is not finding titanium. The challenge is separating it from the other elements to which it is tightly bonded. The process begins with mineral deposits that formed in coastal sand over millions of years. One of the world's major sources of titanium minerals is Richards Bay Minerals, located along the coast of South Africa. This enormous mining complex is among the largest producers of titanium-rich minerals on the planet. Miners are searching for heavy minerals such as ilmenite and rutile, which contain titanium combined with oxygen. Every year, the operation processes more than 22 million tons of sand taken from ancient coastal dunes. However, the titanium-bearing minerals are widely scattered throughout the sand. Each ton contains only a relatively small concentration of useful material, forcing the mine to process enormous quantities. Producing 1 ton of titanium can require about 11 tons of mineral ore, followed by a lengthy chemical process that may continue for months. All this effort is justified because titanium is one of the most valuable metals used in modern engineering. At the mine, enormous dredgers and hydraulic excavators remove huge amounts of sand. The material is mixed with water to create a thick liquid mixture called mineral slurry. This slurry is pumped through pipelines toward a facility known as the spiral plant, where the first stage of separation begins. But how can an ordinary grain of sand eventually become one of the strongest metals on the planet? When the slurry reaches the processing plant, it is fed into a series of gravity spirals. These cleverly designed machines operate somewhat like the pans once used by gold prospectors. As the mixture flows downward through the spirals, gravity, water flow, and motion begin separating the different materials. The heavier minerals containing titanium move toward the inside of each spiral. The lighter grains of ordinary sand move toward the outside, where they are removed. The result is a dark, heavy mineral concentrate containing a much higher proportion of titanium-bearing material. After this initial separation, the mineral concentrate undergoes further purification in a facility known as a dry mill. Magnetic and electrostatic separators distinguish the minerals according to properties such as magnetism and electrical conductivity. These systems remove unwanted materials and isolate a more concentrated supply of ilmenite. Even after purification, ilmenite normally contains only about 45 to 60% titanium dioxide. To transform this mineral into a metal suitable for aircraft, spacecraft, and other advanced equipment, it must undergo the extremely complicated Croll process. Industrial facilities produce tens of thousands of tons of titanium using this method every year. The process begins by converting the mineral into a highly reactive chemical compound. The titanium-bearing material is treated with chlorine and carbon under intense heat. This reaction creates titanium tetrachloride, an extremely volatile and transparent liquid. Once formed, the titanium tetrachloride is cooled, condensed, and collected in liquid form. The next challenge is recovering the titanium by separating it from the chlorine. This is where one of the most expensive stages begins. Another valuable metal, magnesium, must be introduced into the process. Titanium tetrachloride and magnesium are placed inside large, sealed reactors and heated to between approximately 1,470 and 1,650 degrees Fahrenheit for several days. During this period, an important chemical reaction takes place. The chlorine bonds with the magnesium to produce magnesium chloride, while the titanium is released in solid form. Once the reaction is complete, the reactor is transferred to another furnace. A high-temperature vacuum removes the remaining magnesium, magnesium chloride, and other chemical residue. What remains inside is nearly pure titanium, but it does not yet resemble the smooth, polished metal used in airplanes. It has an extremely porous structure filled with microscopic cavities. Because of its appearance, this material is known as titanium sponge. The titanium sponge must then be broken into smaller fragments using powerful industrial crushers. These metallic pieces travel along conveyor belts, where their quality is carefully inspected. Contaminated or unsuitable pieces are removed before the material moves to the next stage. Approximately 330 pounds of titanium pieces are loaded into a special tube inside a compacting press. A massive piston descends and applies several tons of pressure, compressing the loose pieces into dense cylindrical blocks. These blocks are then melted inside a vacuum arc furnace. Powerful electric currents generate an arc that produces enough heat to melt the titanium. The vacuum prevents the hot metal from reacting with oxygen and other gases. After melting and solidifying, the material forms massive titanium ingots. In many cases, the titanium is melted more than once to improve its purity and ensure that its chemical composition is consistent throughout the entire ingot. Once the ingots are complete, the next stage begins, transforming these enormous blocks of metal into useful industrial shapes. Before titanium can be forged, it must first be softened with heat. The ingots are placed inside industrial furnaces and heated to temperatures approaching 2,000 degrees Fahrenheit. At these temperatures, titanium becomes sufficiently malleable to be reshaped without cracking or breaking. When the metal reaches the correct temperature, enormous robotic clamps remove the glowing ingots from the furnace and carry them to the next processing station. There, colossal hydraulic presses capable of applying thousands of tons of pressure begin forcing the metal into new shapes. Under this tremendous force, the ingot slowly deforms. It may be reheated and pressed repeatedly over several hours. The enormous block gradually becomes a long bar, a thick slab, or a large industrial plate. The titanium may then undergo additional rolling, forging, cutting, and heat treatment processes, depending on its intended use. Every stage must be carefully controlled because even a minor defect could become dangerous when the finished component is placed inside an aircraft engine, spacecraft, or other high-stress machine. The final products are exceptionally strong titanium plates, bars, and components, ready to be shipped to factories around the world. There, they may become parts of aircraft, rockets, ships, medical implants, chemical processing equipment, and countless other advanced technologies. What began as scattered grains of dark mineral sand has now become one of the most valuable engineering materials on Earth. Its extraordinary strength, lightweight, resistance to corrosion, and ability to survive extreme conditions make titanium almost irreplaceable, even though producing it requires months of work, enormous amounts of energy, and one of the most complicated metal refining processes in modern industry. Like the video if you enjoyed it, share it with someone who may find it interesting, and subscribe to the channel with notifications enabled to continue learning.